If you deploy standard multi-agent frameworks into production, they will eventually break. Unconstrained systems suffer from context window poisoning, steganographic collusion, and cascading loops. Trusting a large language model to govern its own safety or limit its own cloud spending is an architectural anti-pattern. You cannot prompt your way to predictable reliability. The Nexus v1.1 architecture solves this by stripping agents of their authority. It introduces a strict 8-layer control plane that treats every agent as an isolated, inherently untrusted compute node. To make multi-agent systems safe for enterprise deployment, governance must be removed from the LLM context window entirely and hard-coded into the surrounding infrastructure. Deploying a zero-trust multi-agent OS requires exact dependency sequencing. We use Terraform to enforce this deployment order from the ground up. We begin at the foundation with the distributed state layer, utilizing Firestore and Redis. Next, the agent and tool registry, along with the persistent memory layer, are deployed directly on top of that state. With memory established, the brain comes online. We deploy the context control plane, or CCP, alongside a dedicated observability layer. Above it, we integrate the hybrid execution layer, which actively runs models. We cap this with the governance airlock to audit every generated output. Finally, we deploy the Nexus core orchestrator to coordinate internal routing, sealing the entire stack with the API gateway for external ingress. Building bottom-up through infrastructure as code physically prevents cyclic dependencies. The API gateway cannot accept traffic before the execution layer exists, and no execution happens without isolated state backing it up. Even after a successful deployment, the system does not immediately accept user traffic. Instead, it enters a critical phase called bootstrap validation. The core orchestrator actively polls the health endpoints of the CCP, airlock, registry, and observability layers. If a single core service returns a degraded status, the orchestrator aborts the startup entirely. A hard failure at startup guarantees that we never route production traffic into a partially blind or unmonitored multi-agent environment. Once the system clears validation, we can track a live, potentially hostile user request entering the pipeline. The request hits the API gateway. Here, the text is sanitized for prompt injection, and the persistent memory layer returns a strictly bounded slice of prior conversation history. The gateway packages this sanitized input and memory slice into a structured thread packet. This isolates the context, ensuring no raw data penetrates further into the architecture. The gateway passes this thread packet down to the Nexus core orchestrator. The orchestrator operates under severe constraints. It is entirely stateless, contains zero routing logic, and is restricted by IAM policies from executing external tools. This thin design guarantees the orchestrator acts only as a secure dispatcher. If an attacker compromises a downstream agent, they cannot use the orchestrator to escalate their privileges. The true intelligence of the system lives one layer deeper, inside the context control plane. This is the operating system kernel. The orchestrator delegates the thread packet to the CCP, which is solely responsible for determining how the request is executed. Here, we discard LLM-based reasoning for task delegation. The CCP relies exclusively on deterministic, rule-based routing to choose between a single agent or a swarm. The CCP scans the payload complexity. If it classifies the request as highly predictable and simple, the payload is routed directly to the Model Context Protocol tool gateway for execution by a single isolated agent. Alternatively, if the task is classified as complex or triggers a token pressure heuristic exceeding 1,500 tokens, the CCP forces execution down the agent-to-agent path, initiating a structured planner and executor decomposition sequence. Regardless of the path, the CCP applies uniform security controls. Every payload carries a mandatory trace ID, and all internal calls are restricted by least privilege invocation roles. By routing deterministically, we establish predictable latency ceilings and eliminate the possibility of a language model hallucinating an unauthorized execution path. To verify these constraints, we run a production readiness test, proof the architecture survives hostile conditions. The test parameters require hitting the system with 100 concurrent requests of mixed complexity, while deliberately taking critical infrastructure offline. In our first simulation, we artificially scale a core component, like the registry or MCP layer, down to 0 instances. In a standard multi-agent setup, this creates an unhandled exception loop, sending a cascading wave of HTTP 500 errors back up the chain until the application collapses. Nexus defends against this using distributed circuit breakers backed by Redis. If the system detects 3 connection failures within a 2 retry window, it opens the circuit. The broken path gracefully degrades, while unaffected complex traffic continues routing normally down the functional paths. Distributed, state-backed circuit breakers contain localized agent outages, preventing a single broken node from taking down the entire intelligence stack. The second simulation addresses the asynchronous cost spike. We trigger a rogue agent-to-agent fanout, generating hundreds of redundant tool calls designed to push the per-trace cost over a strict 50-cent threshold. Embedded within the observability layer, the Plutus FinOps module actively monitors real-time cost accumulation. As the rogue swarm amplifies, Plutus detects the budget breach and autonomously fires a hard kill switch, severing the execution trace before it ever reaches the governance airlock. Subsequent simulations prove similar resilience. When we force traffic surges or database outages, the system trips API rate limits and falls back to cached lookups. Across all test scenarios, all requests safely resolved or gracefully degraded. The cryptographic context hashes remained unbroken, and average operational cost stayed under 9 cents per trace. Achieving true multi-agent production readiness does not require waiting for smarter models. It requires deploying mathematically governable, hard-failing infrastructure.